Hello and welcome back. Today we'll be discussing Chapter 19 in versions 1 and 2 of Klein Organic Chemistry, which is Chapter 18 in version 3 of Klein Organic Chemistry. This chapter includes electrophilic aromatic substitution reactions, nucleophilic aromatic substitution reactions, and elimination addition. The better part of the chapter is electrophilic aromatic substitution, which we'll spend the most time on, and we're going to see that electrophilic aromatic substitution uses the same mechanism for all of its different variants. So that makes it a little bit simpler, but there are some caveats that we need to understand in this reaction, and we'll probably discuss those in the next video. So I want to go ahead and get started. In Chapter 18, we discussed aromatic compounds and some properties of them, and we saw that aromatic compounds are less reactive towards something like addition than a regular carbon-carbon double bond. For example, bromine, as shown here, can add across a double bond, and we saw this in our alkene addition reaction. It can add across a double bond, giving us Br and Br in an anti-conformation. We don't get that kind of addition with benzene because benzene is aromatic. It's more stable as an aromatic compound, and to break the aromaticity would give us a higher energy product, and therefore it's difficult to do that kind of addition reaction with something like benzene. But if we use a Lewis acid catalyst, we can actually get what's called a substitution reaction. So we're substituting a hydrogen on the benzene ring for something like a bromine. So we're going to see different variants of the substitution reaction dealing with electrophilic aromatic substitution. So remember that benzene, all of its carbons are sp2 hybridized, so each one of these carbons has one hydrogen. Okay, and we're going to be replacing one of those hydrogens with something like a bromine in this case. For this, we're going to need a catalyst that's going to turn our substituent, the thing that we're substituting on the ring, into a strong electrophile. We need a strong electrophile in order to effect this reaction. So we're going to see all the different variants of this reaction, which include putting a bromine on the ring instead of a hydrogen, substituting the hydrogen with a chlorine, or a nitro, or a sulfonyl, or an alkyl, or an acyl group. So we're going to learn the reagents required to effect each one of these transformations. So basically they're pretty simple: for bromine, chlorine, nitro, sulfonyl, or sulfonyl, but when we get to the alkyl and acyl group, then we're going to see that gets a little bit more complicated, especially the alkyl. And so normally we don't think of something like a bromine acting as an electrophile. That's why we need to add a Lewis acid catalyst in order to create a strong electrophile such that the aromatic ring is nucleophilic enough with its large region of electron density in order to act as a nucleophile. So remember, an aromatic ring, if we look at it, say, on its side, has these p orbitals that are overlapping, and each carbon has donated one electron into each one of those p orbitals, and in such a way the electrons are distributed around the ring in something called resonance, but that high region of electron density actually allows it to act as a nucleophile. So we're going to see that with this electrophilic aromatic substitution. So the overall mechanism is the same for all of these reactions. We're going to start with something that is strongly electrophilic. So here we have Br2. We're going to use a FeBr3 catalyst in order to create this electrophilic species where one of these bromines basically acts as a carbocation, or like a carbocation would, as an electrophile with a full positive charge. So the FeBr3, the iron tribromide, accepts a lone pair from one of the bromines on the dibromide molecule, okay? And that's going to create a strong positive charge on one of the bromines, allowing the ring to act as a nucleophile, attacking one of the bromines and kicking out the iron tribromide with the extra bromine. Okay, and when that happens, the bromine is added into the ring, and now we see that we have resonance around the ring where we have the positive charge at the ortho and para positions. So we've broken aromaticity in this intermediate, and this intermediate is called a sigma complex. In the last step of this mechanism, this species that was kicked out comes and pulls off a hydrogen in order to restore aromaticity to the ring, giving us the product. So the overall reaction is that we're substituting a hydrogen, in this case, for a bromine. So this one is called halogenation. So in order to create that strong positive charge on our electrophilic species, in this case the Br2 molecule is going, one of the bromines adds a lone pair into the Lewis acid catalyst with the iron, okay? And then it creates this bromine with essentially a positive charge, a Br+. And so that Br+ can act as a strong electrophile to allow the benzene ring to be sufficiently nucleophilic to attack it. So in the first step, the benzene ring acts as nucleophile, attacking the bromine with a positive charge, and then aromaticity is broken, and we can draw a resonance structure for the sigma complex. Okay, so the sigma complex has resonance with the positive charge all around the ring. And in the last step, aromaticity is restored by removing the hydrogen that was on the ring and leaving the substituent, which in this case is a bromine. So the iron tribromide is a catalyst in this reaction. So we get substitution instead of addition because the substitution product is aromatic, which makes it lower energy than the addition product. So a potential addition product would be higher energy than a substitution product, and that's why the substitution predominates. We can also use chlorine instead of bromine for this reaction. So instead of the FeBr3, we have aluminum trichloride, where the chlorine, the Cl2, is one of the chlorines is adding in to the aluminum Lewis acid catalyst in order to create essentially a Cl+, just like we had a Br+ previously, and we're replacing one of the hydrogens on the benzene ring with a chlorine in this case. Okay, so if we go over here to our overall reaction diagram, we can write our reagents in that we need to accomplish each one of these reactions. So for halogenation, we have bromination with Br2 and FeBr3, and we have chlorination with Cl2 and AlCl3. Okay. So we don't generally get fluorination because it's too violent to be practical, and iodination is too slow. It gives us lower yields. Generally, we're going to see just chlorine and bromine for this reaction. So the overall mechanism is the same for all of these electrophilic aromatic substitution reactions. We create a strong electrophile, which can be something like a carbocation, it can be a Br+, a Cl+, and the ring is going to act as a nucleophile, attacking that electrophile, forming a sigma complex that has the positive charge in resonance around the ring. And in the last step, something's going to act as a base and pull off the hydrogen that we're replacing with our electrophile. The overall mechanism stays the same for all of these individual examples. So the next reaction we're going to look at is going to be sulfonation. So we can actually put the sulfonyl group on a benzene ring as well. This is the only one of these reactions that we're going to see that is actually reversible. And we're going to use that to our advantage later on in the chapter. So in order to put a sulfonyl group, an SO3H group, on the ring, we're going to use fuming or extremely concentrated sulfuric acid. Okay, so we're replacing a hydrogen with an SO3H. Okay, So fuming sulfuric acid consists of sulfuric acid plus this SO3 gas, which acts as an electrophile. Now this is a electrophilic in a different way. Sulfur doesn't have good overlap with the oxygens in this case because the orbitals don't overlap as well. Sulfur is larger than the oxygen, and therefore the overlap isn't as efficient as it would be from, say, a carbon-carbon double bond. That makes the sulfur electron deficient and therefore electrophilic. So it's subject to attack by the nucleophile, which is the ring acting as a nucleophile, which can attack the SO3, and we get our sigma complex. So at the end, something comes along acting as a base, pulling off that hydrogen that is being replaced in this case, leaving the SO3 group on the ring, which is negatively charged, that can go ahead and pull a hydrogen off and give us our final product. Now again, this is the only one of these reactions that is actually reversible. If we use concentrated sulfuric acid, we get sulfonation. If we use dilute sulfuric acid, we can actually take that sulfonyl group back off and replace it with the hydrogen that we started with. Now we're going to see that this is very important. We can use this sulfonyl group as a blocking group later on in this chapter. So let's go ahead and write our reagents down for that particular reaction. So we have, fuming sulfuric acid. Now remember, this reaction is reversible with dilute sulfuric acid. Okay. The next reaction on our list is nitration, and we can put a nitro group on the ring if we use a combination of concentrated sulfuric and nitric acid. The reason is because sulfuric acid is slightly more acidic than nitric acid, and it will protonate nitric acid. When it does, we get this intermediate, which is unstable, which breaks down into a nitronium ion. This nitronium, or NO2, is highly electrophilic and can be attacked by the benzene ring, which is acting as a nucleophile. So we get the same mechanism where we have our sigma complex, and we have that positive charge with resonance all around the ring. In the last step, something acting as a base comes along and pulls off that hydrogen that we're replacing, leaving us with the NO2 on the ring. Okay, so we've substituted a hydrogen on a benzene ring with an NO2 group. So we can go ahead and write that in, nitric acid and sulfuric acid. Okay. So you can see that very quickly we've gone through all of these reactions, and we only have two more in order to complete our little table. So we're going to see how to put an alkyl group and an acyl group on the ring. I'm going to complete those examples in this video, and in the next video we're going to get into some more caveats of this reaction. Okay. Also, I forgot to mention that nitration gives us an NO2 group on the ring, but if you wanted to add an amino group, if you want to add an NH2, you can get that from a reduction. So we can use iron or zinc in the presence of hydrochloric acid, and that's going to reduce the nitro group to an amine group. So if we want to put an amine group on a benzene ring with electrophilic aromatic substitution, we can do that in a two-step process. We can use nitric acid and sulfuric acid to put the nitro group on, and then second we can use zinc and HCl to reduce that nitro to an amine. But we can't put the amine group on directly with electrophilic aromatic substitution. So let's go ahead and write that in as part of our chart. Okay. So we're going to use zinc and HCl to convert our nitro group to an amine group. So the next reaction is alkylation, and in this case it's called a Friedel-Crafts alkylation. And this reaction is going to put an alkyl group on a benzene ring. Now we haven't seen too many ways up to this point to add a carbon chain to our molecule. So we've seen a few of those. We've seen a Grignard reaction. We've studied alkylation of an alkyne with an alkyne. We've also seen using a cyano group as a nucleophile in an SN2 reaction. But this is another way to extend our carbon chain to add an alkyl group to our product. Now, this, I think the slide here meant to say ineffective electrophile, so there's an error here on the slide. But we don't normally think of alkyl halides as being electrophilic enough to allow a benzene ring to actually be a nucleophile and directly add this alkyl group onto the benzene ring. Okay, that would be a very unusual situation. But we can make that alkyl group, that alkyl halide, electrophilic enough by adding a Lewis acid catalyst. Now this confuses some students because the catalyst looks very similar to the one we used. In fact, it's the same catalyst that we used in just a regular chlorination or bromination. So here we have a chlorine as our alkyl halide, so in order to avoid any kind of side products, we'll use aluminum trichloride as our catalyst, and that's going to make our alkyl halide essentially electrophilic enough in order for this reaction to occur. Now you can actually alkylate with just a straight carbocation, and you've seen some ways to create those. We don't cover them too much in this chapter, but in our lab we actually performed a similar reaction with just a carbocation, where we actually used dimethoxybenzene, and we created a T-butyl carbocation that could then add into the ring itself. And it actually adds twice because this reaction is very favorable. And we got this for a product. Now this carbocation wasn't created through the use of a Lewis acid catalyst. The carbocation was created from T-butyl alcohol, which was protonated with sulfuric acid. And because it was protonated, this tertiary carbocation was able to form pretty easily, and that was actually acting as our electrophile for our reaction that we did in lab. But generally for Friedel-Crafts alkylation, you're going to use aluminum trichloride as your Lewis acid catalyst to create your electrophile. So same thing, the chlorine with its lone pairs, one of the lone pairs can add to the aluminum, which is a Lewis acid, and creating this species here where it dissociates into what is essentially a carbocation plus the negatively charged aluminum species. Now the carbocation is pretty much a full carbocation, and it can undergo rearrangements, and that is the disadvantage to a Friedel-Crafts alkylation. If your carbocation is able to rearrange, it will. And so here you see that we've created a primary carbocation. So with this aluminum trichloride and this chlorobutane, we're going to create a primary carbocation. And since it's primary, it's subject to rearrangements, and our major product then is actually the rearranged product, which we get in a 65% yield as shown here, or a 35% yield with the primary carbocation. Okay, so that's one of the disadvantages of the Friedel-Crafts alkylation, is that carbocation rearrangement which can occur. And so we're going to see that the acylation will actually avoid that rearrangement. Okay, so another limitation to Friedel-Crafts alkylation is that the halide leaving group has to be attached to an sp3 hybridized carbon. So if we try to use an sp2 alkyl halide, we're not going to get a reaction. Or something on a benzene ring, for example, we're not going to get a reaction. And also, like I mentioned earlier, polyalkylation can and does occur. If we add one alkyl group to the benzene ring, we're going to often add more than one alkyl group to the benzene ring, and that's because one alkyl group actually speeds up the reaction and makes it more favorable. And so when we add that first one, we're going to have a tendency to add a second one. Now, if you have a deactivator, which we're going to talk about later, on the ring, then it's going to deactivate the ring toward electrophilic aromatic substitution. And if you have something as electron withdrawing as, say, a nitro group, you're going to get no reaction because we really need that benzene ring to act as a nucleophile. And if you have an electron withdrawing group on the ring, that's going to destabilize that nucleophilic tendency. So acylation and alkylation are both forming a new carbon-carbon bond. We just looked at alkylation where we're putting basically an R group on the ring. We can also see that we can put an acyl group on the ring. And this is actually a better method if you can get rearrangements. So if you add an alkyl group on that's not going to rearrange, then that's fine. We don't need to worry about doing an acylation. We're going to see that requires an extra step if you want to put an alkyl group on the ring. But if you have something that's going to rearrange, generally the better way to do that is to put that acyl group on the ring, and then we can just reduce the acyl group in a similar way that we did the nitro group earlier in order to get our alkyl group in the end. So the acylium ion forms basically in the same way as our carbocation did, as our Br plus did, as our Cl plus did. The chlorine that's attached to this acyl chloride will actually attack the Lewis acid catalyst, forming this intermediate species that decomposes to the acylium ion, which has our positive charge, so it acts as a good electrophile, but it is also resonance stabilized and therefore won't rearrange. So you see here the acylium ion is resonance stabilized and not subject to rearrangement. So we get, if we use our Lewis acid catalyst and an acyl chloride, we can add the acyl group onto the ring, and then if we really wanted the alkyl group, we simply reduce with zinc and HCl to get our product. So that reaction is called a Clemmensen reduction. And by the way, the acylation is called a Friedel-Crafts acylation instead of a Friedel-Crafts alkylation. So an acylation followed by a Clemmensen reduction, I'll just say reduction, is a two-step process for adding an alkyl group that would otherwise rearrange onto the ring without rearrangements. So we can go ahead and add those reactions with our reagents to our little chart. So we need an R, say Cl, and FeCl3, that's our catalyst, to get the R group on there. And we can also have, let's say RCOCl and FeCl3, and that's going to put our acyl group on the ring. And I'll write on here, subject to rearrangements. Okay. Another advantage to adding an acyl group onto the ring is that it's not subject to polyalkylation, and that's because the acyl group is actually electron withdrawing, and therefore it deactivates that ring toward further acylation, and so we tend to just get monoacylation, which reduces unwanted side products. Okay, so that covers everything I wanted to talk about in today's video. Next time I'll go on and talk about activating and deactivating groups and what happens if we already have a group on the ring and we want to put a second or a third group on. We'll see how that's going to affect reactivity. Thanks for watching and have a great day.